Enterprise planning today relies on a shared, incredibly high-speed bedrock to power its massive operations, the SAP HANA in-memory database. Yet, even with this shared technical foundation, different business domains require entirely divergent data architectures to function. SAP Integrated Business Planning, or IBP, is built specifically as a highly specialized operational engine. Its core purpose is to manage the physical supply chain. SAP Analytics Cloud Planning, or SAC, operates as a lean, agile engine engineered for unified financial and driver-based planning. Understanding modern enterprise architecture requires us to deconstruct their distinct data schemas, their calculation processing engines, and version control mechanics that dictate specific system capabilities. Selecting the right planning tool requires matching the data model to the exact nature of the business problem, resolving physical constraints versus modeling financial states. Operational systems require highly specific data blueprints to function. In SAP IBP, this blueprint is centralized in a concept called the planning area. This planning area diagram brings together discrete master data types, binding them to specific key figures. To map physical realities, IBP maintains highly nested relational interdependence. This complex architecture is bound to multi-dimensional time profiles, calculating intersections across specific days, weeks, or months. Financial data warehousing takes the opposite approach. SAC planning relies on a classic star schema. This star schema layout features a central fact table surrounded by isolated dimension containers, tracking elements like sales organization. SAC binds financial data tightly to accounts within this table. By extracting only the baseline essence needed for decisions, it creates a minimal data footprint. IBP's deep relational schema maps the tangled reality of physical goods. SA's star schema is intentionally stripped down to maximize multidimensional slicing and dicing for financial agility. The underlying schema strictly dictates how a system processes data. For IBP, this means utilizing an algorithmic constraint engine. This visualization illustrates IBP's heavy-duty supply chain algorithms in action. Using heuristics and mathematical optimization like CPLEX, the system calculates and routes material flows. These algorithms incorporate demand sensing to calculate capacity limits and determine safety stock levels. To maintain constraint awareness, logic only processes at explicitly assigned intersections, calculating demand exclusively at the customer product level. SA utilizes a distinct processing paradigm that prioritizes financial and driver logic over physical optimization. To calculate financial positions, dynamic variances, and currency translations, SA relies on data actions and script-based advanced formulas. This equation demonstrates the explicit mathematical logic SAC uses. By multiplying deal value by probability across iterations, it builds a probability-weighted pipeline forecast. SAC calculates outputs on the fly, eliminating the need to maintain hundreds of rigid, hard-coded rows for calculation permutations. IBP engines solve for spatial and physical limits. SAC engines solve for dynamic financial states based on changing mathematical variables. Because they solve different mathematical problems, these two systems require entirely divergent levels of data granularity. IBP tracks exact distribution hubs, specific machine resources, and precise SKU-level movements. SAC relies on aggregated dimensions, using flat hierarchical lists to allocate quotas. This difference in granularity controls how each system handles version management and scenario modeling. Looking at this supply network, we see IBP's real-time system feedback. If you increase demand on a key figure, it instantly ripples through the engine to flag physical capacity deficits. Instead of real-time alarms, SAC approaches versioning by prioritizing safe, entirely isolated, sandboxed environments for its users. Here, a central fact table is cloned to create a private version. Users instantly isolate data for pipeline simulation and ad hoc visual modeling. Inside this private version, users run gap analyses and manual overrides without affecting the core data footprint. Once the financial model is ready, these private versions publish out, coordinating seamlessly with a centralized warehouse layer like SAP DataSphere. Operational changes trigger immediate alarms to prevent physical supply chain failures. Financial modeling requires strict isolation until a strategy is officially finalized. Modern enterprise planning does not force a choice between physical optimization and financial agility. It demands their integration. SAP IBP wrestles with the complex physics of the supply chain, processing physical constraints and raw volumes. SAC planning acts as the flexible financial umbrella, interpreting that physical reality into actionable fiscal strategy. This diagram demonstrates the standard architectural flow. Operational variables are mathematically resolved in IBP, and the resulting data is pushed cleanly into SAC to drive integrated financial forecasts. A financial forecast is valid only if it is physically feasible. By mapping the correct schema to the correct problem, an enterprise achieves both operational constraint awareness and strategic financial agility.